applications of integrals. So you already know one application, so which is if we need to find, say we have XY plane. So if we have a function, right? And if you want to find this area, right? If function is above x-axis, so this area equals to integral from a to b f of x dx, right? So that's the first example of application. That's what you're familiar from calculus 1. So we'll do something similar here. And we'll do application of integrals, which we'll be doing all the time. So the way the calculus is working. So you want to find something, you find approximation to something that you want to find. What you will do is, instead of finding the whole thing, you divide the whole thing into small pieces, then you approximate small piece, you add up all approximation, you get approximation to a whole big thing. And then you take limit of your approximation. So each small piece, you get even smaller pieces. And you take that approximation, take limit of approximation. Eventually you're going to get integral, and integral will give you the answer. Okay. So this is an idea. Okay. So idea. Okay. So idea is the following. So you need to figure out something, right? You need to figure out something. So something. Okay. So what you'll do is you divide that something into smaller pieces. Okay. So you divide into smaller pieces. Okay. So something which we did in when finding area, what we did is we did our rectangles, right? So remember these pieces, right? So, and then approximate each piece. Approximate each piece. Then add up all approximation. Add up all approximation. So when you add up all approximation, we're going to get f of xi delta x I from 1 to n. And that is going to be Riemann sum. Okay. And then the last step, take limit when delta x approaching 0, right? Riemann sum. And we're going to get definite integral. Okay. So we're going to get definite. At least that's an idea. So divide into smaller pieces, approximate each small piece, add up all the approximation, you're going to get sum. Take limit of a sum, and then they get limit of a sum, we're going to get definite integral and stuff. So, okay. So just keep in mind the following. When we're taking limit, when delta x approaching 0, we're taking that limit, our sum becomes integral, delta x becomes dx, xi becomes just x, because xi tells you, you go through particular points, and when we making delta x to disappear, we will go through all points, and yi will become just y. And lower limits will be where you start, and upper limits where you finish. So you see that n becomes upper limit. So that's b, and I equals to 0 becomes lower limit. x equals to a, and sigma becomes integral. Okay. So just keep that in mind. That's how usually we're going to transfer Riemann sum into an integral. Anyhow, that's what you should probably be familiar with from Calculus 1. Just a quick reminder. And now we'll try to do an example related. So say I guess I have like a cap here and I want to calculate its volume. So I have a circular base, circular thing on top, right? So let's pretend it looks like this. It's not exactly like that because it's a little bit convex, but let's pretend it looks like this. And we want to calculate its volume. Okay. So to do that, we need to figure out what will be radius on the bottom. What will be radius on top? And what is the height? Okay. So let's say ball. It's about 3 inches, my best guess, and about, I guess, 5 on top, diameter, I mean. So radius will be 1.5 and 2.5 inches. And height, 1, 2, 3, 4. Again, my guess is about 6 inches. Okay. And we want to calculate what will be the volume of that cap. Okay, so let's see how we're going to address this situation. Let me try to graph it. So when I'm going to graph it, I'm going to put it sideways. So I'm not going to be putting it sideways. I guess I'll do just that. Okay. So sideways, I'm going to spill my tea. So I'm going to put it sideways. I'm putting that cap sideways. Do you see the cap? Okay, so hopefully we see the cap. So that is X, that is Y. If you like, I can put numbers. So for example, here I will put 1.5. This point, if I put it down here, it's 6. And if I put on that side, it's going to be 2.5. So if you like, that point has coordinates 6 and 2.5. So we'll need those numbers eventually. But firstly, let's get an idea. So what I want to do is, basically, I want to do is something similar to what we did with area. I'm going to divide it. So the way I'm going to divide it is I'm going to make slices. So I'm going to slice. Just imagine like you did, if you go to a deli and you order your sliced cheese or sliced jerky, then it's going to be sliced. So that's exactly what we'll do. We're going to slice it. Okay. So we're going to slice it. Okay. We're going to make slices. Right? So we're going to make slices. Okay. And then we're going to pay attention to one particular slice. So we're going to slice it. And then we look at one slice. A slice is going to look something like this, right? So I'm going to now draw a slice. Not much better, but a little bit. So that's how a slice is going to look like, right? Now I'm going to approximate each particular slice. So area, volume of a slice, approximately equal to. So what I will assume is, I will assume even though here our edges are not perpendicular, right? Edges are not perpendicular. I assume that is perpendicular. So I'll assume that's area of base times height. Area of base times height, in this case, is times thickness. Base times thickness. Okay. Thickness comes from, because let's look again at that picture. How am I going to get that thickness? Thickness comes because I'm doing these slices. When I'm doing the slices, when I do these slices, right? So what is going to happen is I'm going to slice x-axis. So I'm going to get delta x to be thickness. So thickness is delta x. Again, the reason, because I'm slicing, right? And when I'm slicing, I'm going to get delta x. Thickness is delta x. Area of cross section or area of base. If you look at it, it's circular, so it's going to be pi r squared because circle. Because circle. So we get volume of a slice. Approximately equal to pi r squared delta x. And I'm going to put I here because it's like volume of I slice, volume of particular slice, right? So then I got total volume approximately equal to sum I from 1 to n pi r squared I. So again, I sliced it. I pay attention to one particular slice. I approximate one particular slice. Volume of it. I figure out what the thickness is, what delta x is. If you look at the picture, then you also probably can figure out what will be r. R is, let's look, r is from here to here, right? So if you look at this picture, r is from here to here, right? So r is y coordinate of a point. So r equals to yi. Because that is radius. And if you return to original picture, that's what we're going to get. Ri. So I guess we can rewrite our formula one more time. Total volume approximately equal to sum I from 1 to n I y I squared x. That is our approximation. Then we take limit of approximation with delta x approaching 0. When our slices become thinner and thinner and thinner, we're going to get better and better approximation to volume. So eventually we're going to get exact value for volume. So that's going to be total volume. And as we discussed earlier, we're going to get volume equals, when we take in limit, sigma becomes integral, pi is pi, yi becomes y, square is square, delta x becomes dx. And we need to figure out where we finish and where we start, and where we finish. Okay, so let's have a look where we start and where we finish. we start our slicing here, right? And we finish our slicing here. So you see we start slicing, and when we do slices up from this point, right, from here, when x equals to 0, and we finish our slicing at the right side, so when x equals to 6. So we're going to get from 0 to 6 for a limit of integration. Okay. And it's tempting to write down that the value of antiderivative y squared will be y cubed over 3. But unfortunately, we have dx here, which tells us that we have to finish our substitution and write everything in terms of x. So let's look at our picture one more time. So y will come from this straight line. So let's copy that picture maybe here. So it's 1.5 here, and 6 and 2.5 here. And then we have that straight line. Because you remember where it's coming from. It's coming from this type of picture, right? That's what we did. So we had 6 here, and we had height in diameter of top is 2.5. So we have that. Now, if you look what is here, is that a straight line? It has y-intercept 1.5. Slope is 1 over 6. Run is 6, rise is 1. So we have equation of a straight line y equals 1 over 6x plus 1.5. And that's exactly what we wanted for y, right? Because that's our y, and that's y. It's going to be substituted here. Then we're basically ready to do the calculations. Equals to integral 0 to 6 pi. Y is 1 over 6x plus 1.5 squared dx. And that is a reasonably easy enough integral. We can calculate this integral using substitution. U equals 1 over 6x plus 1.5. Or we can do it by using algebra by taking square of 1.1 over 6x plus 1.5. So decide which method is better for you, which is easier. It looked to me that substitution will be the easiest way to do the calculations here. So I'll do substitution u equals 1 over 6x plus 1.5. Then du equals to 1 over 6 dx. Then dx equals to 6 du. And because I'm working with definite integral, x is changing from 0 to 6. U, which equals 1 over 6x plus 1.5, will be changing. So I'm substituting 0 for x, I'm going to get 1.5. And I'm substituting 6, I'm going to get 2.5. So that's my substitution. If you pay attention to what is going on, you actually notice that what we're doing is we're actually doing substitution y equals, right? So actually that u is y. So we kind of switch into everything to y. So we're going to get integral u equals to 1.5, u equals to 2.5 pi u squared, and dx equal to 6 du. So 6 u. So our antiderivative will be pi u cubed over 3, 6. U is equals to 1.5, u equals to 2.5. equals 2. So our final answer is going to be 2 pi times 2.5 cubed minus 2 pi times 1.5. So I guess graph our calculator, do the calculations. At least I got 24.5 pi, which is approximately equal to 76.969 inches cubed. So volume over cap is approximately 77 inches cubed. So that was integral. So integral, we should be familiar how to do calculations. So when you think is getting that integral, that's a new thing. Okay, now let me summarize what we did. And maybe we'll do the write down shortcut formula if you like. So let's see. Dx here because we were slicing x-axis. Okay. Because x-axis is sliced, so what's obviously that's dx. Where we start slicing and where we finish slicing, right? What was the first position, what's the last position? So between which two values of x, right? Between which two values of x we do slicing? We start somewhere here. So we start somewhere here and we finish somewhere there. So starting and finishing position is kind of obvious. Integral sign is integral sign. So I guess one thing which is maybe still confusing, where that pi y squared come from. Let's try to see where that pi y squared comes. It's this stuff, it's that stuff, and where it comes from, it comes from here. So you see that's area of cross section. And that is area of cross section. So that stuff is area of cross section. It just happens that in our case, we get area of cross section to be circular, so area of cross section will be pi r squared. So if I will summarize what is, I'm going to get the following. So when slicing perpendicular to x-axis, when slicing perpendicular to x-axis, volume is going to be equal integral. Again, that's where I start. X equals to A, X equals to B, that's where we finish. So start slicing, finishing slicing. Then here we get area of cross section. I get the area of cross section, it should be somewhere. Cross section. Dx. Okay. So that's what we do if we do perpendicular to x-axis. When slicing perpendicular to y-axis. So let's look at the picture. So we're going to slice y-axis. So we start somewhere, y equals to c, we finish somewhere at y equals to d, and then we start making our slices. Right? I'm not sure how a slice is going to look like. We're going to get slices. So volume is going to equal to integral. We start at y equals to c, we finish at y equals to d. Because we slice in y-axis, we're going to get dy. And here it's going to be still the area of cross section. Okay. Not sure how a cross section is going to look like. We're going to get something